Hello friends, let's design a layout for the CMOS inverter using microwind software. So as soon as you open the microwind software, you will be seen with this window. So this is a normal menu bars, file, view, edit, simulate, compile, analysis, etc. These are the shortcuts to open new file, save. Then you can move and stretch icons, and as and when you select the component and it is required, then this shortcuts you can utilize. So if you click here, this is a palette. So palette is a window wherein we can get different layers for designing of the inverter, NOR gates, various digital logic circuits. They are provided with PMOS, NMOS. This is a MOS generator. Then in order to add the virtual capacitor, resistor, inductor, then voltage source, VDD, ground connection, add a clock, and this is to add any node so as to observe the waveforms at the output during the simulation. Fine. Now we'll design the CMOS inverter. Before actually going with designing of CMOS inverter, we'll have just a brief introduction of CMOS inverter. So CMOS inverter, as it's a complementary metal oxide semiconductor MOSFET, it has one PMOS and one NMOS. 2W indicates W/L ratio for PMOS is preferred to be twice as that of the W/L ratio of the NMOSFETs. So source, gate, drain for PMOS, drain, gate, source for NMOS. So both the drains are connected together and from the common terminal output is taken. So this is a capacitor which is connected across the load. So it will help in deciding the rise and fall time in the output waveform. So A is the input where we are providing the input, either logic 0 or logic 1. So as per the truth table, for the input of logic 0, we will get output as a logic 1. For input of logic 1, output 0, wherein this logic 0 state is equivalent to 0 volts in terms of electrical parameter. For logic 1, we are assigning the VDD which is equal to 5 volts. So we can assign here VDD to be equal to of 5 volts also. So let us consider for this case, the VDD is equal to 5 volts and equivalent logic 1 state voltage is also equal to 5 volt. It may vary based upon the design. So just check carefully here how the connections are made. Source, gate and drain. Source of PMOS is connected to VDD. Now all these things we will reflect in the designing of its layout using the microwind software. Now let's go back to designing of our layout. So let us initially choose from the MOS generator, I will click MOS generator. So it is asking me directly PMOS. So PMOS W/L ratio, I will prefer it to be double. So width is of 1 micrometer, length is 0.1 micrometer, let it be as it is. I will just click on generate the device. So it will generate the device. So device has been generated, layout box has been gone to the upside from the window. So I will take help of this see upper layout. So the block will be appearing down. Along with this one PMOS, I need one NMOS to make the complementary pair. So I will click on NMOS. So I will make its width to be of 0.5 micrometer and then generate the device. So device will be generated here. See, now I want to bring this back to back, one below each other, because we know that gate of both the transistors are connected together. So you can use this icon. It's not giving me the label. Yes, stretch and move. This is stretch and move. So I will select it. So this has been selected and I will keep it exactly down to that of the PMOS. So this is a PMOS, this is NMOS. Now I want to join these two. Gate of PMOS is joined with gate of NMOS. That is what the structure is. So how to join this? I can use this polysilicon layer that is used as a gate terminal for designing of the gate. So I will join these two with by selecting the metal. So with the polysilicon, I have joined gates of both the transistors PMOS and NMOS. Apart from that, we have seen that this is a P MOSFET. So this is the source, gate and drain. I will mark this as a source, this as a gate and drain. Again we have seen source of the PMOS, it is connected to VDD. So I will stretch this element also. So metal 1 and metal 2. Even I can go just select this box, stretch and move. Let us see how it works. Okay, it is not extending in this direction. I will select this block. Oh, so Control U for undo option. I think this should be metal. If I select metal 1, again this is Control U. Okay, I will join the drain of both the transistors with this metallic layer. So drain of both so this is a source, gate, drain for PMOS, and this is a source, gate and drain for NMOS. So I should choose this metallic layer, so second layer, using which I can extend this. Oh, this is also wrong. Metal 5, let me check. Oh, okay, let me stretch this part, that is source. Let me stretch the source terminal of PMOS. So this is source. Now we have seen according to this diagram, see the source of PMOS is connected to VDD and source of NMOS is connected to ground. So accordingly we will follow. So this is the VDD connection, VDD supply. So VDD supply will connect it to the source of PMOS. Along with that, every time by default we have to connect the VDD supply to the N well also. Now ground is to be connected. So ground, source of PMOS, source of NMOS is connected to the ground connection. Now from this we can take the output. Common drain, we can take the output. So again I will choose this metal part to take the output. Even if you don't extend the layer, that is okay. But for the convenience of understanding, I will choose. Now I will add one node here. So this node is, I will call this as a V out, where we'll be observing the output. So assign, that will be visible in the output. Along with that, to check the input with respect to which output will vary, so clock 1 I will choose. So I will call this as a input A. Again I will assign this and it will be visible in the output node. So input, output and the ground connections are over. So this is the only circuit. This is a rule checker, design rule checker. So this is the design rule checker. Let us check. No design rule error. So 0.7% memory is being used. Now if we simulate this, we will be observed with waveforms. So these are the waveforms. They change the scale. So these are the waveforms, input and output. So this A indicates it's the input, V out is the output voltage. We can change the scale to see the details clearly. So this is the input and this is the output. So for input of 1 we are getting output as a 0. For input of 0 output is 1. So let us consider here the highest voltage is 1.2. So 1 and 0. So these are the waveforms of voltage versus time. So if we see voltage versus voltage, it indicates that with respect to input voltage, the way input voltage is less here. So for 0 input voltage or slowly increasing value of input voltage, the output voltage is high. For the higher values of input voltage which are towards the logic 1 state, for this we are getting output to be equal to 0. So these are the transition characteristics, that is V out versus V in for the NMOS transistor. Now let us see the effect of, so this is the what we have seen, voltage versus time. So make a note of the slope. So voltage versus time, we are getting this waveform. It is almost a straight line. Now let us check the effect of connecting capacitor. So again from the palette, let us choose the virtual capacitor. and place it here. Check its value. Its value is 0.01. Let us keep it as it is. It is observed. Now if we simulate this waveform, we should observe the change in the waveforms, that is in its rise time and fall time. So instead of straight line, so the rise time, so this is the rise time and the fall time. There is a slight variation in the rise time and fall time of the output waveforms after connecting the capacitor. With capacitor of 0.01 picofarad. Now if we simulate, initially we should save these changes in the layout made and then do the simulation. So if we simulate the circuit, it will show us waveform. See, this is the change. What is the change? So if I change the time scale again, see the rise time and fall time. So this is the rise time when the state inverter is changing the state from output of the inverter state, it is changing from 0 to 1 and 1 to 0. This is the rise time and fall time. So these are the changes observed in the rise time and fall time after connecting the capacitor. So as you change the value of capacitor, such changes will be observed. Now this is of 0.01 picofarad. So if we change the value, so if we change its value from 0.01 to suppose 0.03, the effect will be same. So if I will save the changes, and now if we simulate, see the waveform has been changed now again. So rise time and fall time. As we increase the value of capacitor, it is fast charging and again discharging, but it is not a sharp such a change. So the value of capacitor, if we make it as low as possible, virtual capacitor as a load, then it is moving towards the exactly square waveform. So by changing the value of capacitor, it allows us to change the rise and fall time of the inverter output.